In this video, we'll look at the dislocations in HCP metals. Since HCP metals, they have lower symmetry compared to FCC and BCC metals, so the dislocation activities will be more complicated. A commonly observed slip system is the basal slip. The basal 0001 plane is shaded in red, and this arrow shows the Burgers vector. In addition to this Burgers vector, you have two more equivalent Burgers vectors along this and this directions. Since the Burgers vector is along the A direction of the crystal, the 112/0 direction, this is also called the basal A slip. Another very common slip system is the prismatic A slip system. In this case, you have the same Burgers vector, but it glides on the prismatic plane. By the way, I made a mistake here. The prismatic plane is not 0001, it is supposed to be 101/0. Now, let's look at some less common slip systems. Again, we have the A dislocation here, but it can also glide on the pyramidal plane. The pyramidal plane is 101/1, as shaded in purple here. Besides those A dislocations, you can also have dislocations with the 0002 as the Burgers vector. Because the Burgers vector is parallel to the C-axis of the crystal, these are also called the C dislocations. My understanding is it is not known on which slip plane those dislocations will glide on. C dislocations are speculated to be decomposed from C plus A dislocations. The Burgers vector of C plus A dislocations can be viewed as the red arrow plus the blue arrow, so it's inclined. So the Burgers vector is 1/3, 112/3. C plus A dislocations can glide on the pyramidal plane, same as the pyramidal A slip plane. In this case, it is called the pyramidal 1 slip. C plus A dislocations can also glide on the 112/2 plane. These C plus A dislocations are called the pyramidal 2 C plus A's. Note, both pyramidal 1 C plus A and the pyramidal 2 C plus A, they have the same Burgers vector. In addition to dislocation activities, you can also have deformation twins. The extension twin has the twin habit plane 101/2, and it contributes to the C-axis extension. You can also have compression twin or contraction twin with the twin habit plane 101/1. Note the twin plane is the same as the pyramidal 1 plane. Contraction twins can accommodate C-axis compression. I hope this information is not overwhelming. If you do not do research in HCP metals, you don't have to worry too much about it, as long as you know the deformation mechanisms are complicated in HCP metals. Let's revisit the two most commonly observed slip systems, the basal A slip and the prismatic A slip. For different HCP metals, they have different C/A ratios. When C/A is large, that means A is small. The most packed planes are the 0001 planes, so basal slip are usually prevalent in those metals. A good example is magnesium and magnesium alloys. When C/A is small, that means C is small, so the prismatic plane is the most packed plane, and the prismatic slip is easier, and it will become prevalent. The typical example is another lightweight metal, titanium. After discussing the perfect dislocations in HCP metals, let's look at stacking faults in HCP metals. Regarding stacking, HCP metals are very similar to FCC crystals. If you look at the 111 plane in FCC, it has the ABC stacking. If you look at the 0001 basal planes in HCP, they have the AB stacking. For the HCP metals, you can have the intrinsic fault and extrinsic fault. Let's look at the first case. You start from the AB stacking, then you have a C stacking, and after that you have BC. This is called the I1 fault. I stands for intrinsic. In the example on the right, you start from AB stacking, then you have the C stacking, then you have AC stacking after that. This configuration is called the I2 fault. Let's do a really quick comparison. For the I1 fault, you start from AB, then you have CB. For I2 faults, you start again with AB, then you have CA faults. The common feature is after the stacking fault, you will never return back to AB-AB stacking. You can also have extrinsic fault. Again, you start from AB-AB stacking, then you have C, then it returns back to AB-AB. Note, in the extrinsic fault, before and after the fault, you always have AB-AB stacking. You can view that as inserting an extra plane into the perfect crystal. One thing I'd like to draw your attention to is the areas near the stacking fault. You have ABC, ABC, ABC stacking in all three cases. And if you recall, ABC stacking is the FCC stacking. What this tells you is for HCP metals that contains stacking faults, very, very locally, you have a very thin layer of FCC crystal structure. Since my research focuses on magnesium, I'll share with you some of the TEM micrographs I took when I was working with Professor Hemke. By tilting the crystal to different diffraction conditions, we can reveal A, C, and C plus A dislocations. The yellow dashed lines indicate where the C plus A dislocations are. They appear to be basal bound. Then the blue curve shows where the C dislocations are, and the green dashed lines indicate where the pure A dislocations are. In the next video, we'll move away from metals and look at dislocations in more complicated systems.